Okay then. So now we do the second part, which is the hardware programming. We're going to have exactly the same application as before. But in the moment we talk about hardware programming, whatever you see here is only designed for that kind of application. So if I'm going to have another one, I have to redo the wiring so I have another design. For that particular application, I prepared for you a diagram over here, and I'm going to quickly explain it, because if I don't, it's going to be difficult to understand what do I want. Anyway, for this application here, I'm going to have just one button over here, which is going to be the stop start, or if you want the start stop, okay, to control what happens, which is going to basically be my power supply. Then I'm going to have this red button over here, which is loading my counter with the number I want. So for the purpose of compatibility with the other version with the PLC, I set up here the same number. Remember, 111 or 0111 in decimal converted is 7, okay? And this is the button to load the number. And then I can use two ways to start counting the items, because again, that's a simulation. One way is this green button, exactly like the green on the other side. So take a look what happens when I press the button. From 111 is going to go to 110, which is 6. You see it? It's counting down. Then to 101, you see? 101, 100, 011, which is 3, 010, which is 2, 001, which is 1, and now 0. And now you hear the buzzer. And the buzzer is simulating the motor going on the conveyor to pick up the box with the items and taking them out, okay? Second option, the number is loaded again because I just pressed the red. So in the moment I press the button, obviously the buzzer stops. And then instead of using the green button here, I'm going to have the same kind of sensor we used before. So the same photocell we can use to count. And this one here, if you take a look, it already has a little LED, a green one. The green one only says that the cell is operational, is energized. And by the way, this kind of cell I chose, it can be energized with any voltage between 10 and 30 volts. For that reason, I wired all the diagram using CMOS packages, so they work very fine at 12 volts. 12 volts is above 10, so everything is going to work just fine. And in the moment the cell is operating, in other words, I put my hand in front of it, or is the simulation of the fact that an object is passing in front of it to be counted before reaching the box, you're going to see another light over here, not only the green showing the functional cell, but the orange is the signal telling that everything is counted, okay? So you have two lights. Green is energized, the cell is energized, and the orange to say we count, okay? So now I'm going to load the number again, the same number 7, and then I'm going to count. 1 is going to go to 6 because 1 out of 7 is 6. Counting down, next is 5, 101, 4, 100, 3, 011, 2, 010, 1, 001, and 0 when you see all the lights off. And by the way, for the control, anytime I press either my green button here, you see, the first light on the left, the first LED on the left is just saying exactly like on the other side I had a blue light signaling that. Anytime a pulse is coming, you're going to see the first LED going on. And here there is a second light, and this second light is going to stay on as long as the cycle of counting, like in our situation, the 7 pulses are passing. So when we reach the last one, like is 1 next time, is going to go off. Take a look. Everything goes off, okay? So that's how we know everything is done. Now the next thing is, what do I do if I'm not happy with the number 7? Let's say we are just changing the box on the conveyor to fit 12 items and not 7. What do we do in that case? I'm going to put the cell away. In that case, I have to explain to you something on the diagram, which is something new regarding the same kind of counter we used before, the 193. And when I presented the 193, I said it can be a TTL, which is 74-193 or 74LS-193 or 74ALS-193, or it can be HC, 74HC-193, which is high-speed CMOS, or it can be HCT-193, which is high-speed CMOS TTL compatible, or this one here, which is really CMOS 40, 193, has the same pin out as the TTL, but you can energize it 12 volts. And I had all the packages, just a couple of packages, there are not too many, to do this thing to happen. But now, how do you set the number? Because this thing we didn't do before. I said before in other videos that by using the pin 11, which is called load, if you are connecting it to plus 5 volt or to the VCC, in our situation 12 volt, you can keep counting. But this has an interesting function. The counter itself, not only it is able to count up and down, not only it is able to give you a signal on the borrow output or on the carry output, depending how you count. We use the borrow now because we count down. This is anytime you want to combine that counter, actually to cascade this counter with another one to count to bigger numbers. And this is used when you want to count down the borrow. And this is an output. But the input load is interesting because it's allowing, when put in 0, to use some other inputs I didn't mention before. I mentioned them now, which are called A, B, C, D. So I put them in the descending order because this is how you read the actual number, DCBA. And there are the pins 9, 10, 1, 15. And these are called parallel inputs because the counter is a pretty smart one. By putting this pin 11 load in 0 logic, when I press this button here shortly, as you can see, there is a resistor connected to 12 volts. And by pressing the switch, that point here in the middle, when I press the switch, it goes to 0, to the ground. So then it's going to touch the pin load. Exactly when I press it, like here. I press it, take a look what happens. I load the number 7. Why 7? Because the 4 wires here, I put them 0, 1, 1, 1. Let's say I want to change them and I want them to be 1, 1, 0, 0, which is exactly like on the other side of the PLC, the number 12, okay? So take a look what I'm going to do. I have the orange and the yellow wire, both 1, 1, and I'm going to have the green and the white ones. I'm going to put them in 0, okay? So then when I press this red button, instead of seeing here 0, 1, 1, 1, so the LED which is off on the left side, the fourth LED, is going to become 1. Take a look, 1, 1, 0, 0. This in decimal is going to represent the number 12. So now when I'm starting either from here, 11, remember from binary 1011 is 11, 1010 is 10, 1001 is 9, 1000 is 8, and so on. Now 7, no, 6, 5, 4, 3, 2, 1, and 0. I reload the number, it's still 12, obviously, because it's hardware set this counter. How is this set? By just modifying the binary inputs DCBA from here. Please make the distinction between these letters DCBA and these ones from here, because the letters DCBA here are actually the outputs Q, D, Q, C. Remember, the Q is the letter used anytime you have a flip-flop or a counter or a shift register. We use the letter Q just to prevent the confusion, because if it was O from output, O may be easily confused with a 0, especially like for people like me having an ugly writing style, okay? So now we're going to do the same using the photocell, because I moved the photocell for you to see it over here, okay? I'm going to reload the number, it's 12. So now I'm counting 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, and then the buzzer. You see this? I reload the number, okay? If I want to reload that number to another one, let's pick up another number, like let's say I don't want 7, I don't want 12, I want, I don't know, 5, okay? For the number 5, what do I have to do is to put the most significant in 0, then it's 1, 0, 1. So when I start here, 0, 1, 0, 1, this is 5. So anytime I'm going to count, I'm going to pick up my cell, because I moved it already. It was supposed to stay on the conveyor, but I'm moving it to be seen. I reload the number. So I put the hand in front of it. Another little detail, it doesn't matter I positioned it to the light. It's not sensitive, because anytime you put the hand, let's say at too big a distance like here, the number, as you can see, doesn't change anymore. That particular cell has a sensing distance up to 1 foot or about 30 centimeters. So anytime the object is passing at a bigger distance, it can't be seen, because you don't want objects to be falsely counted when somebody passes on the corridor, let's say. So the object has to be pretty close. So anytime you need a sensor, you're going to buy it for the distance you actually need. So now it's 3, 2, 1, 0. That's it. Okay. So anytime I want to reload the number, I can count either using the photocell or using the green button, exactly like I did on the other side. And now let's find out quickly on the diagram how this one is operating, in case you want to replicate that little experiment, because it's extremely intuitive. It's working exactly like the one on the PLC, but I had to re-modify the diagram here because it's not the PLC here. We just have a simple diagram. So then, here is the counter, the brain of this diagram. And the counter has here 4 outputs in the button, QD, QC, QB, QA. It has the 2 pins for the power supply, VCC pin 16, respectively ground the pin 8. We don't need to use the reset for this one. So the clear or the reset is grounded because we don't use it. We don't need to use the count up, so the count up is related to the plus 12 volts, sorry. And we only use the counting down, okay? The other control pin available is the load, because this is the red switch over here. I wrote it here, red push button, PB stands for push button, okay? So this is the one, and the green one is over here. This is the green push button. So now, in order for me to use the green push button and the photocell, by the way, this is the symbol for the photocell. Just a mention, in a moment you want to use such a photocell, you have to connect a resistor here for 12 volt. It's about 22 kilo ohms is a good value between the output and the 12 volt. So in other words, the photocell needs 3 wires. 2 of them are used for the power supply, ground and 12 volt. And the third one is the output of the sensor, which is connected to the input of that inverter here. So this is because I found in my junk box a NPN sensor. So this is the one with 1 foot or 30 centimeter sensing distance. Being an NPN sensor, I connected it through an inverter. So then, how do you connect the push button and the sensor to be able to be connected in parallel? You need to connect them through a gate. What I prefer to use is a exclusive OR. So the package number is 4077 because you can only use one at a time. In the moment you accidentally want to use both at the same time, the output is going to stay 0. If you don't have this one, 4077, which is exclusive OR, you can use a simple OR, which is 4071. But you have to be careful then not to press both at the same time. Nothing wrong is going to happen, but the gate is going to be confused. Okay? So you have a choice. Either you use a exclusive OR, 4077, the pin number for the gate is the same, or the 4071, which is a simple OR. Either of them you can connect here. So then you have access to use the photocell and the push button. The push button is for the troubleshooting in case you have any trouble to do the wiring for the photocell. And then what happens, they are connected here through 2 gates. why there are two gates actually needed an AND. But the package 4011 I'm using here, it contains 4 identical NAND gates. And 2 of them I used over here, I circled them. They are together in a simple RS flip-flop. The RS flip-flop, remember, this is the reset input, this is the set input. It has the output, the normal output Q, and the complementary output Q bar. What happens is, you set the number from here, from the parallel inputs, by pressing quickly the red button. So the load goes 0 for a fraction of a second. You load the number. So in the counter is going to be, let's say, the number 7. And then when you press the countdown, the number is actuated, so it's going down. In the moment it's reaching 0, that borrow reaches the value 0. So what does it mean? If you connect it to the reset input of the flip-flop, what does it mean, the reset? You put the normal output in 0. So by putting this one in 0, the normal output, take a look, is a wire coming over here. So by having this input in 0, whatever is coming from here, so pulses from either of these two, the counter won't operate anymore. So the counter stops at 0. That's the point of having an RS flip-flop over here. But when this output is 0, obviously the complementary output is going to be 1. So I'm using this one logic to put in saturation a little transistor, just to make sure whatever kind of buzzer you have with any consumption, 50 milliamps or 100 milliamps or even 1 amp, it won't matter. That's the symbol for the buzzer. So then the buzzer is going to be connected because the transistor in saturation collector emitter voltage goes to 0. So it's like the buzzer is going to be connected between the ground and plus 12 volts. So when I'm keeping counting like this, and the buzzer is operating now, if I'm continuing to count from here, you see the signals are coming, but they are not counted because here there is a 0 logic preventing this gate to operate. So you have to press the button to reload the counter, and then here you're going to find the 1 logic. This is why I monitored on the LED here a 1 logic for the troubleshooting, to allow you seeing that the number is loaded and the flip-flop was not reset, it was set, because when you press the load, 2 things are happening. When you press the load, you load the number here, but at the same time when the signal goes 0, even for a very short time, you put the pedal down, the called set. And what does it mean set for a flip-flop? The normal output goes in 1. So having a 1 here, it allows pulses to come and to operate. So in the bottom you have 6 LEDs. You can put 6 independent LEDs as you wish. I prefer to use from a bar graph 6 LEDs, and some of them are not in use. I use all the 4 on the right side and the 2 on the left side, so the ones in the middle I'm not using. So these are the LEDs, the 6 LEDs I'm using from my bar graph. Here are the resistors, these ones, 820 ohms for a 12 volt. If you energize everything from 5 volt, you need to lower these ones to about 330 ohms. But then you have to be careful because your sensor, this one here, won't operate anymore. I mentioned it before that the sensor to be operational, it needs at least 10 volts power supply, okay? So this is how the diagram is working. And obviously, I'm going to put it on Google Drive. Everybody's going to be able to download it. So then if you want to replicate that little diagram here, keep in mind that you need just few packages, but for the next project we're going to discuss later on, I have to modify the diagram. This is the meaning actually of the hardware programming. So we were doing before software programming, now this is hardware programming, and I wanted to show you that you can have actually the same application on both. Now, what is the difference between them? Why did I do it in 2 ways? The advantage of using the PLC is that anytime you want a new application, you only have to design a new program. You don't have to modify practically anything about your wiring. What is the catch? The catch, there are 2 actually. First is you have to invest to have a PLC. Not only to have the PLC, but to build the trainer. Remember, I have a whole series of 22 videos only about how to build a trainer. with a PLC. And then you have to build a second trainer for your PLC, the trainer for the outputs. So you have to invest some money to have that PLC ready. Once you have it, then any kind of application you want to simulate, you only modify the program. And the second catch is that you have to become familiar with the programming using that application coming with the hardware, with the PLC. So there are advantages and disadvantages. Now here for this one, what is the advantage? Is an obvious one. If you only want to make this little project, you only need about $10 or less, excepting for the photocell, which is a bit more expensive. But you can easily find another model which is similar to this one for about $15, okay? And you can use it. So it's very easy and cheap to build. What is the catch? You want to build another project, you may need other packages, other integrated circuits, and you need other lights, or you may need displays and so on, like the display, the double display we built in the previous project. So you actually need to invest also in some components and to have a rack somewhere. When you need components, you have to extract them from there. So for each kind of way you make your application, software programming with the PLC or hardware programming with integrated circuits, there are advantages and disadvantages. So then, hoping everybody's okay to understand what I presented today, if you want to make that project working, you are going to find the diagram on Google Drive. And please be ready for the next project we're going to make next time. Thank you very much for your patience. See you next time. Bye-bye.